All right, let's talk about work, and specifically an example of filling up a spherical tank with water. Okay, first of all, let's review work is force times distance. When we're talking about moving water, how do we get force? Well, force is pounds. Well, how do we get pounds from moving water? Well, we take the density times volume. That will be pounds. And then times distance. So we're going to just try to add up all of these. Density times volume times distances. And do some subdivisions, but then the number of subdivisions approach infinity. And we recognize this as the definite integral. So density, volume, distance. And of these things, density, that'll be given to us. And most of the time, if you're talking about water, you're talking about 62.4 pounds per cubic feet. If it's like oil, it might be less. That would always be given to you in the problem, though. The density would be given, the liquid would be given. The volume, that's what we're going to have to think about a little bit. And we think about the cross-sectional area and the thickness, and that's where our differential comes from. And the distance that the water has to be moved or pumped, that's usually very logical. It's usually just one of the variables, and then maybe plus a constant, say if you have a tank on top of a pedestal, that kind of thing. So really the work that we're going to do probably is mostly related to the volume. Okay, let's talk about a specific example. Let's say we have a spherical tank that has a radius of 20 feet, and it's full of water. And let's say water is going to be pumped out the top of the sphere. How much work will it take to empty the tank? And assume the density of water is 62.4 pounds per cubic feet. Okay, we know work is force times distance. And force is going to be density times volume. The density we know is 62.4. We just need to figure out volume. Okay, so let's think about as I pump water out, the water takes on the shape of the container. In this case, the little shapes of water are little discs of water. The cross-sectional shape is this little cylindrical disc. Well, I know how to find this volume. The height of this thing is our differential, and I just need to figure out the radius and take pi r squared thickness. So when we're thinking about our integral, the thickness, that's our differential, dx. Okay, there's a couple of decisions we need to make here. One is, where's our variable? And I like to have my variable start at where the first sliver of water is coming from, and then work down the container. So in this case, I'm going to have x equals 0 be here at the top, and as I work my way down, here at the bottom, this will be when x is 20. And if I do that, well then the distance is just the variable x. At the top, how far does this piece of water have to move? Well, 0. And once I get to the bottom, how far does this piece of water have to move? It has to move 20. So I'm going to have x go from 0 to 20, and then my distance is just x. I'm going to take this 62.4 and put it out front. That's constant. That's the density. And actually I'm going to take this pi and pull it out front as well, because that's also constant. So I've got my density, I've got my distance, I've got my thickness. I just need to figure out a relationship for the radius squared. You might think, oh, the radius is 20. Well, let's just put 20. But is that true? Is the radius constant? Is the radius 20 the whole time we move down this sphere? It's not. If you have the radius constant, you're actually just doing a cylinder. That's what a constant radius would look like the whole way down. And this is not a cylinder. So we need to think about a relationship. So let's go here and just think about a circle for a second. If I just look at this cross-section, if I know the radius of this sphere is 20, and we said that we're going to start x at the top and move down. So this is x, and so the radius of the cross-section is this. This is the radius of the cross-section. As we move down these cross-sections, this is the radius. Well, how would I figure that out? Well, it's pretty tricky, but it's pretty nifty, also pretty slick also. The radius of this sphere is 20, right? Well, that means that this distance here is 20. And if this part here is x, how much is left over for this part? Well, 20 minus x. And now we have this right triangle that we know two of the three sides. I know this is the r I'm looking for. This radius is 20, and this is 20 minus x. So we could use the Pythagorean theorem to figure out r. So we know that r squared plus 20 minus x squared will equal 20 squared, and we could solve for r squared equals 20 squared minus 20 minus x squared. And actually, if you remember our formula, we're looking for r squared. Well, here it is. We found it. And if you want to simplify this, this is 400 minus 40x plus x squared, which simplifies into 40x minus x squared. That is r squared. And so let's go back and let's just put that right here. R squared is 40x minus x squared. And then this would be the integral that would compute the amount of work to empty all the water out of this tank. And at this point, you would use your calculator or your computer to figure out the value of this integral. A lot of times these questions will be set up, do not evaluate, or if it is, I mean, this wouldn't be that hard. We'd have to use the power rule. I guess we could use a u substitution. You could use a u substitution, let u equal this. Here would be kind of a du, but that'd be kind of ugly. We could FOIL this out and then distribute and just use the power rule. But at this point, we've already proven we can find out these integrals by hand. At this point, we could just leave the integral or use our calculator to find the exact value.